Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is our last lecture, lecture 24. Today, we're just going to extend some of the concepts we introduced in the last lecture on conditional distributions to now the continuous setting, where pretty much everywhere we see a distribution, we just replace it with the word density to reflect the fact that somehow and almost magically, you can always just what you would normally do with probability do the same thing with the density function, and things work out to be roughly the same. We'll go ahead and see where the law of iterated expectations shows up in this sort of setting. And then I want to introduce two really important canonical problems that occur in the study of continuous probability. One is the stick problem, which basically asks, if I have a stick and I break it once, and then I break it again with the longer portion or the first part, how do I determine what is the distribution of lengths? This somewhat shows up if you think about rock formations in a cliff. Things tend to fall, and then that causes other things to fall below it. And again, it shows this process of there being sort of a two-step occurrence here. And so you're trying to study what the output is, but you know that it's conditioned on the input. And that input is itself a random variable. Finally, we'll talk about how do we really do science, especially when we're given, let's say, a coin that we don't know if it's biased or not. Perhaps it's an alien coin, and we just don't know how alien coins flip on Earth. What happens when I need to do some really solid statistics to decide what is the probability distribution for getting a certain number of alien heads out of a certain number of flips? And then how do I figure out what that probability is after I've just done like a few samples? As you can see, this all builds into like the key part of doing statistics, which nowadays sits inside of what's called the Bayesian framework for inference. And for any of you that are going to keep studying probability or statistics in the future, or go on to become engineers or scientists or doctors, understanding these concepts is, I think, really important. And that's why we're going to spend some time in this very last lecture together to go through it. All right, so let's get down to it. And let's just sort of remember what's a typical setup for a problem that involves continuous probability. As we usually do, we like to study situations where, let's say we have two random variables, which sort of behave jointly as a uniform probability on some sort of region or shape. For example, we might have something that looks like this. So this is what I'm drawing here is the support of a joint probability density function, a JDF or a JPDF, where I've got x equals 1 over here and y equals 1 over here. So immediately we know that the joint density function for big X and big Y looks like 1 over the area for points in the support, and it's 0 otherwise. The support, again, being the set of points where this joint density function is non-zero. Well, if you remember the formula for area of a triangle, it's 1/2 base times height. Base and height are both 1 here, so the area is 1/2. So this ends up equaling 1/2, which means that my JDF is 2 everywhere in that green triangle and 0 outside of that. So here's a quick practice question for you. And this is typical of something you might see on the final. Suppose you pick a point at random. Where random is defined in terms of this this JDF. So the probability of picking a point out here is 0. But the probability of picking a point in any small region here is proportional to the area of that small region. And the density there is 2. So you pick a point, and now you form a rectangle using that point by connecting the opposite point to be the origin. What's the expected area of this rectangle? Formed by that point and the origin, 0, 0. If you think about it, this is actually just a word problem for computing the following integral, which is you want to compute the expectation of x times y. Because we know for a rectangle, the formula for the area is height times base. Here the base is x and the height is y. Now, I'll go ahead and set up this integral, maybe do the first few steps, just so you know how to start it, but I'm going to leave it to you to finish. All right, so I've got my integral here. Now, again, it's a double integral. So you need to figure out, how do I evaluate the limits here? If you choose to slice, let's say, vertically, that means you've got to find a condition where it enters the support, which in this case is y equals 0, and then where it exits the support, which in this case is 1 minus x. Once you've done that, you've essentially marginalized out to get a PDF for x, and then now you just need to integrate this PDF of x. But everything here is now weighted by x times y, so there's an extra factor. So just set up the integral for you. It's y equals 0 to y equals 1 minus x. And then we're integrating that from x equals 0 to x equals 1. And because we're trying to find this expected area, I need to take this function of x and y, which in this case is just x times y, multiply it by the PDF, little x, little y, integrate from dy dx. So in this case, we get something like, all right, x equals 0, x equals 1, y equals 0, y equals 1 minus x. I know that f of x, y is just 2. So this ends up pulling out as a 2. And now I just need to integrate x times y, dy dx. All right, so here I first hold x constant and I integrate with respect to y. You'll see that you get like a y squared divided by 2, whereas you need to plug in this formula and simplify. All right, so the rest is on you. All right, now why might you want to compute this? And go ahead and feel free to pause the video and try to work out this integral. All right, well, once you've taken that time, let me just also mention why you might want to do this. So we try to get at the question of why do we care? Well, one thing to note is that when you want to compute the covariance of two random variables, x and y, this is equal to the expectation of x times y minus the expectation of x times the expectation of y. This ends up being our detector to determine whether or not x and y are independent or not. And in the case that they're not independent, sort of how correlated are they? Because correlation, the sort of intuitive concept from statistics that we use in our day-to-day lives, actually, if you look at the formulas for it, involve using this covariance formula. So understanding this covariance formula in the settings could be really important. But we also know intuitively that X and Y are not independent. So I'll just go ahead and phrase that here. Again, what we're looking at here is this JDF where it's uniform on this triangle, f of x, y is equal to 2 and 0 otherwise for x in the triangle, x and y in this triangle, and then 0 otherwise. So let's answer the question, are x and y independent? Well, we can actually just stare at the support of this and realize that they're not independent. In particular, if I compute what's the marginal PDF for x, that means I have to integrate this function out. That's going to tell me the probability density of this point x. And then if I were to integrate this out, I would get the probability density for y at that point. Now, if I take this pair of points x and y, I'm going to get something like, all right, let me do it sort of farther out here. So probability density here at x, probability density here at y. If these were independent, I could multiply these probabilities, these numbers, which I see are both non-zero, and I'd get a non-zero number here. But obviously that doesn't agree with the JDF. And it's no, because f of x, y, which is a function of x and y, is not equal to f of x times f of y. So that's a quick check. And in particular, you can just look at the support and determine that this is true, at least in this case. Here's another way to sort of look at this, and this is to study the conditional density. All right, so how is this defined? So the conditional density function of x given that y equals some value little y is sometimes denoted by f of x conditioned on y, little x conditioned on little y. And this is by definition going to be the JDF of x and y divided by the JDF, or sorry, the PDF for y, assuming f of y little y is not equal to 0, because otherwise this expression is going to blow up. So you just need to sort of add into the conditions on the definition of this that this is only defined where f of y is not 0. All right, cool. Now, what does that look like in this particular example, and why is this connected to independence? So notice if x and y are independent, then we know that f of x conditioned on y, little x conditioned on little y, is going to be equal to f of x times little of little x, f of y of little y, divided by f of y of little y. So then these guys go, and this ends up being the distribution, the PDF for x, which again makes sense. If x and y are independent, then knowing y is not going to change the probability density for x. Normally in the discrete setting, we'd say it wouldn't change the probability for x. But again, the miracle of continuous probability is that whenever you think of probability in the discrete case, you can just think of probability density in the continuous case, and things tend to work out. All right, so let's go ahead and work out this conditional density for the example I just introduced. So just as a quick reminder, we're going to condition on y equaling a certain value, and then see how that changes the probability distribution for x. Obviously it does, because we know that if y is here, for example, this value is not possible because it's outside of the support. But let's see how it's reflected in our math. All right, so one of the things we have to first do is compute the marginal for y. So this is the PDF for y. Obviously, if you look at the formula, you need to know that. You need to know what f of y is. Right now, all we have is the JDF. All right, so step one, compute PDF from y by marginalizing. All right, so what that means here, again, is got my little green triangle here. And I'm going to pick a slice like that. And then I need to evaluate the integral over that. So what do I get here? Well, I get that f of little y evaluated at this value y is the integral from x equals 0. Now again, let's go to figure out what's the formula for this point. Well, I know that y equals 1 minus x. So that if I rewrite this, this means that x is equal to 1 minus y. And this kind of makes sense, because if y is all the way up here at the peak here, 1, then I don't need to go very far. I mean, I don't go any distance. I just stop at x equals 1 minus 1, which is 0. All right, so let me write x equals 1 minus y. And again, I'm integrating the PDF here, the JDF, which is dx. All right, so what does that give me? Well, I get 2x evaluated at x equals 0 and x equals 1 minus y. And so I just plug in and I see that I get 2 times 1 minus y. And this works as long as y is between 0 and 1, and then it's 0 otherwise. So that's great. So I've now determined the PDF for y. Let's go ahead and compute the conditional PDF now. So step 2 here. Plug in PDF for y into the definition of f of x given y, little x, little y, which again is the JDF divided by the PDF. So what do we get here? We end up getting 2 times over 2 times 1 minus y. The 2's end up going, and this ends up equaling 1 over 1 minus y. All right, and so notice that this actually isn't a function of x. In particular, this is just going to be a uniform distribution on the segment from x equals 0 to x equals 1 minus x. Let me just go ahead and draw the picture for you again. So you have this. We've conditioned on big Y equals little y here. And so if I look down at the projection here, I know that this is from 0 to 1 minus y. And so what we have here is now that the conditional density is uniform on this segment. So again, this is for x between 0 and 1 minus y. So sometimes you'll be given a specific value. If given one. Let's say we're given that big Y equals 2/3, for example. Then what do we know? We know that the conditional density of x given y, so this is the conditional density for x given that big Y equals 2/3, is going to be 1 over 1 minus 2/3 for x in this region, 1 minus 2/3, which ends up being a third, and then 0 otherwise. And of course, you can see that this ends up simplifying to 3. Sorry for the quick intermission. So continuing, we see that by conditioning on the value that y equals 2/3, that we have now this conditional distribution for x. So let's go ahead and then see where we can take this. We've already observed that, of course, you can look at whether or not x and y are independent just by looking at this conditional PDF. Does it agree with the PDF for x? If not, then we know that there is some relationship between x and y and that they are not independent. All right, so just to sort of summarize, this conditional distribution satisfies everything that we normally think about with continuous probability. So here are some of the usual formulas. These are things like, if I want to know that the probability that x is between some pair of values a and b, conditioned on the information that y is equal to little y, then I can get this answer by integrating from a to b the conditional density function for x, conditioned on the value that y equals little y. So little x, little y, dx. This again expresses the idea that although densities are not probability, you integrate densities to get probability. Additionally, if I want to compute, let's say, any expectation of, let's say, some function g of x conditioned on y equals little y, then I'm just going to integrate g of x over the entire range, but again, where this is multiplied by the conditional density. All right, let's see where this comes up in a couple examples. Maybe since we've got it right here, we can do it in the setting here. What's the expectation? Oops. What's the expectation of x conditioned on y equals 2/3? again, this should be fairly intuitive because we know that we've got a uniform distribution. So this is uniform. Zero to 1/3. We know what the expectation of this is going to be. It's going to be the difference of the endpoints divided by 2. So we should see something like a sixth. In the general case, what does this look like? If I were to look at, say, the expectation of x conditioned on y equals little y, then what I'm doing here is I have to integrate from 0 to 1 minus y, x times this conditional, f of x given y, little x, little y. Now I'm integrating over dx. So in this case, I've got f of x conditioned on y is 1 over 1 minus y. So since I'm integrating with respect to x, y is a constant. So I can just pull out that denominator as if it were like a number. And so now I have x squared over 2 is the antiderivative. And I now get over 1 minus y, x squared over 2, evaluated at x equals 1 minus y, x equals 0. You need to plug in x equals 1 minus y. Notice I've already got, so it's going to be 1 minus y squared. This is 1 over 1 minus y. So when I plug it in, that 1 minus y is going to drop out. And so then I end up getting 1 minus y over 2. So that ends up being the conditional expression there. So notice a couple of things. One, this function, the expectation of x conditioned on y, is a function of y. So just like we did last lecture, you can ask, well, what is the expectation of this function? Now we're sort of letting y vary, and then we're multiplying by the probability that y equals y. This is, again, this expression of the law of iterated expectations. So notice that is a function of a random variable. And so then this gives us the law of iterated expectations. Just back this over here a little bit. All right, so what does that mean in this case? So observe from the last example that e of x conditioned on y equals y is a function of little y. which we know is just being the output of some random variable, capital Y. So the probability that that capital Y equals little y is given, at least in density terms, by the PDF. So this gives us a new random variable, which we can then do things like, what's the expectation of it? So this is actually, we think of it as a g of y, for example. So now you can do things like compute the expectation of it. Every random variable you can consider I should say for every random variable, you can consider its expectation. So what that leads to is considering what is the expectation of this random variable, which we call the expectation of x given y. It turns out that this ends up equaling the expectation of x. And so this is just this right here is sort of an amazing fact. So this is a random variable. And now when you consider the expectation of this random variable, you end up getting the expectation of x on itself. So this is an amazing formula. Amazing. This is especially amazing in situations where, again, we're working in this sort of two-step process, and we don't want to actually compute this directly. So this is useful. This is useful when computing the PDF of x is hard, because then you can get this by instead working with this. Let me give you an example where this occurs. So this is what I like to call the stick problem. So now we have the stick problem. The stick problem basically looks like this. So I've got my stick here, and I choose a location where to break the stick. So step one, pick a location to break the stick. So in the setting where, let's say this endpoint I'm calling 0, and I'm calling this endpoint here 1, just think of this as a unit length stick, then this first step here involves me picking a place to break. Let's denote this by y. So this is break number 1. So this is y, and it's uniformly distributed on the interval from 0 to 1. Again, we can think of the uniform 0, 1 by looking at open endpoints rather than closed. It doesn't actually really matter here. What is step 2? So pick another location on what remains to break again. So you kind of want to think of this as like, you've got your hand here. All right. It's a bad hand. So I'm just going to pause this. Sorry about all the interruptions. Ice cream truck summer is officially here. So just continuing with this example. So we know that we've got this setting where we've got a stick. We're going to imagine that we're holding it and in a hand. Let's say it looks something like, here's this. I've got my thumb wrapped around it, but then I'm also, I've got my fingers around on the other side. All right, so there's my fingers. There's my thumb. All right, so I'm holding my stick. I pick one location to break it, and then I pick a second location somewhere in what's left. This is X. That's going to be break number 2. Now the question is going to be something like, what's the expected length of the stick that I have left in my hand after I break it twice? We know that the probability distribution for X conditioned on Y equaling little y is going to be actually uniform on 0 to Y. But how do we incorporate the uncertainty of Y into this calculation? So let me show you how it's done. All right, so there's a couple ways of getting at this. First of all, I find it useful to always sort of draw what you know, sketch what you know. So first of all, we have to think about what's the relationship between X and Y. And ideally, we can figure out, what's this joint density function for X and Y. So again, this is X and this is Y. Now, we know that X is always going to be less than Y because we're only breaking from what's left. So what this means is, if I've got, imagine this is 1. So my distribution is concentrated on the support. Is a set of points where 0 is less than or equal to X, which is less than or equal to Y, which is less than or equal to 1. But this is not uniform. It is not uniform. How do we determine what the PDF is or the JDF for X and Y is? Well, there's a couple things we can do. One is we could just essentially use the sort of conditional formula for X given Y. So how to determine well, the answer is we want to use this basic expression for conditional probability, which is that f of x, y can be viewed as the probability of x, given that y is equal to little y, x conditioned on y, times f of y at y. Now, you might think, hold up. We just spent the first part of the lecture talking about what this is. And the way we defined it was this divided by f of y of little y. Aren't we just going to chase ourselves around in circles? Well, the difference is, what do you know? If you already know the JDF, meaning you know this, then you can define this in terms of this divided by f of y little y. But you can also sometimes be given this, and then you can use it to figure out this by just sort of multiplying. So what does it look like in this case? Well, we've got something that looks basically like this. F of x given y. So we know that f of x given y, little x, little y, looks something like 1 over y for x between 0 and y, and 0 otherwise. And moreover, we know that f of y, little y, well, that's just got to be the PDF for y, which in this case looks like the uniform distribution. So it's 0 times y for y between 0 and 1. So i.e. f of y equals little y is what we might call the indicator function on this interval 0 to 1. So this is the indicator function. All right, let's go ahead and try to approach some more things. So let's try to figure out, for example, what is the PDF for x? And let's see if maybe we can use this also to compare with how would we compute the expected length. All right, so let's maybe actually start with that second question. What is E of x? So let's first apply the law of iterated expectation. Says that E of x given y is equal to E of x. All right, so we need to figure out what is this E of x given y business. Well, we actually kind of know what, at least what E of x given y is. So remember, it's going to be the integral of x times f of x given y And so what is this? This ends up being, again, if we look up here, 1 over y times this, 1 over y over this interval. And that also dictates how far x can go. So let's just try to do it here. So this ends up equaling something like integrating from x equals 0 to x equals y of x times 1 over y dx. Now, again, y is just a constant for the purposes of this integral. So I can now just figure out that, all right, well, this is the same thing as integrating x from 0 to y dx. But then this is just going to be x squared over 2. Now I need to evaluate it at the endpoints. So let me just go up here. So that's x squared over 2, 1 over y, x equals y, x equals 0. Obviously, plugging in x equals 0 is not going to do anything. It's just going to give me 0. But plugging in x equals y, it's going to be y squared over 2. I have to divide by y. So I end up getting y over 2. So I've now figured out what is the expectation of x, assuming that y is some given value. So now I need to view this as a function of my random variable and now integrate over the density function of y conditioned on or just in the PDF of y. So the expectation of the expectation of x given y. Well, there's two ways of thinking about this. Well, one, I can just recognize that I now have a formula for this expression. And that expression is, let me just do it in red. It's y divided by 2. Oops. So luckily, since I know that y is uniform on 0 to 1, I know that actually this, this expectation can just be computed as 1/2 expectation of y, which is itself half. So it's a half times a half is a fourth. So that ends up being like the super simple way of doing it. But let's go ahead and write it out sort of the longer way. So the longer way applying definition of the expectation of g of y says that, okay, this has to be the same thing as the integral of what we found back over here, which is that the expectation of x given y equals little y is y over 2. So now this is y over 2. And I'm integrating times the PDF, which in this case is just the indicator function on 0, 1 dy. And so normally this is from minus infinity to infinity, but the indicator function is 0 outside of 0 to 1. So this ends up equaling the integral from 0 to 1 of y over 2 dy. And so just working through this real quick, we see it's y squared over 4, evaluated at 1 and 0. And that gives us exactly what we want. We want a fourth. So these two answers agree. So that's good. Math works. Now, let me show you how you would have to do this the really long way. So now the really long way would say, okay, what is e of x? Well, it's the integral of x times the PDF of x dx, again, from minus infinity to infinity. And we need to find this. Don't know. So how do we find the PDF for x? Well, we need to use the following formula. And it looks something like this. So f of x little x equals the integral of f of x conditioned on y, x conditioned on y, times the integral times f of y, now integrate out dy. Now again, this is just another expression of marginalization. And the convenient thing here is we don't work directly with the JDF. We instead work with the fact that the JDF is going to be equal to this. So let's go ahead and do that. All right. So in this case, this equals and again, it's useful to think about what is the support of what's going on here. All right, so I'm trying to integrate in this direction. And I'm integrating with respect to y. So pick a slice, a little x. Now you see that if I'm integrating with respect to y, I have to start at y equals x and I end at y equals 1. All right, so let's do that. So we're now going to integrate from y equals x to y equals 1. And I've got this conditional PDF, which looks like 1 over y. And then I have to multiply it by whatever that indicator function is. 0 to 1 for y. Now this allows me to basically say that any point in here is valid, but I really know that I have this extra constraint, which is that actually y can only be between x and 1. So this actually has no bearing on the integral. So instead I'm now just down to integrating y equals x 1 of 1 over y dy. Now, how do you integrate, or what is the antiderivative of 1 over y? Think for a little bit. Hopefully you'll remember that this is the same thing as the natural log of y. And now I need to evaluate this at my endpoint. So y equals x and y equals 1. Now, natural log of 1 is 0. And then I need to subtract natural log of y evaluated at x. So I end up getting negative natural log of x. That's actually my PDF. Now, if you think about this for a quick second, so remember, natural log looks something like this. And the place where it crosses the y-axis, that's at x equals 1. Which means that if you flip it, I now have negative natural log of x. And I'm conditioning, of course, on the fact that x has to be between 0 and 1. Now, we should be careful here because we already know that this function is not defined at x equals 1. And so we now know that this PDF, which stretches up to positive infinity, is going to be my PDF for x. That should strike you as a little surprising because it somehow tells you that in terms of density, probability of where you might break x or break the stick again is getting closer and closer towards your hand. And that just sort of maybe intuitively makes sense. Like if you pick a point somewhere on the stick, all right, of course, this actually goes to explain why the expectation is a fourth. If you intuitively pick somewhere on your stick, you're gonna, on average, hit middle way through. So now you have a stick that's half the length. So now you repeat the process and you go ahead and take what is the expectation of where you might hit again for your second time, x. This ends up being a fourth. So somewhat amazingly, we already know what the expectation of x is going to be just by intuitive reasoning or by using the law of iterated expectations. Now, the more surprising thing is that we can actually say that this is the expectation for this random variable whose PDF is ln of x, natural log of x. So just to sort of give you a quick idea of how you would compute this the long way, well, e of x would then be the integral from 0 to 1 of x times negative natural log of x dx. And so how do you do this? Well, you'd have to integrate by parts. U dv equals uv minus v du. And here you'd set that u is equal to, let's say, natural log of x, and dv equal to negative x dx. Then you'd have to do some L'Hopital to figure out, well, how is this evaluated? This is 0 and 1, this is 0 and 1. That means that actually this function is evaluated at 0 and 1. And there, when you evaluate the endpoints here, it turns out that this ends up all going to 0. So then you're just down to this, but it's finicky. And you should just take a step back and realize, wow, it was very useful that I could do this law of iterated expectations. But if you really want to check your answer, I would say go ahead and finish this. Especially if you need some comfort in figuring out how it is to integrate these kinds of functions. Okay, so we're at a sort of natural pausing point, but we still have one more topic I want to do, and I want to sort of take a step to look again at Pitman and sort of compare what do we know and what do we don't know. So let me just sort of pause and sort of separate here. And let's take a quick look at, how we kind of compute these things here. So if I copy this, you'll see that I've got all these principles for computing joint probabilities, conditional distribution, conditional expectations. This is all stuff we did in last lecture. And in particular, we saw, again, this law of iterated expectations, which is really highlighted here. So let me go ahead and just paste this into our notebook here, so that we can maybe make some of these comments. And each of these has a sort of corresponding partner in the continuous realm. And it basically looks like this. Again, it might look a little scary, but you basically take wherever you saw P, you now replace it with F. That means you're replacing probability with probability density. But everything else pretty much goes through. So I just want to go ahead and record that for posterity's sake here. So again, we have now this sort of dictionary between, whoops. So here's the dictionary between discrete and continuous. Or discrete and continuous. And now we're looking at conditional probability. And so let me just go ahead and add a few sort of remarks here. So, all right, so these things right here are sort of obvious. They're just how do you determine joint density functions? So let me just sort of call this the JDF rule, and this sort of being our JMF. Back up here. So here's our joint. And then here's my joint density. So sometimes we call this the JMF here. And then we call this the JDF here. We also have our formulas for just conditional, which essentially just is the definition of how conditional probability works. And then, of course, we have the all-important Bayes rule, which is going to be the thing we're going to look at now. But just going ahead and rounding out things, if I want to know what the distribution of probability is, given that, let's say, x equals some little x, then I can always sort of just sum up over all the points in B, or in this case, I integrate. So here, this just sort of illustrates the principle that sums go to integrals. And then everything else is just what to do when you're not dealing with a function. And finally, to sort of summarize here, this last line is exactly the statement that the expectation of the expectation of y given x is equal to the expectation of y. These are sort of called our law of iterated expectations. Cool. So that's great. So let's now take a moment to focus here on Bayes' rule. Because Bayes' rule is really at the heart of science. And so for this, I want to consider a sort of classic problem, which goes at, what do you do when you don't know if a coin is fair or not? And of course, by fair, we mean here, a 50-50 chance of either getting a heads or a tails. So the obvious thing, if you just think about it a little bit, is, well, you obviously flip it. And we know what the rule is for determining what is the number of heads out of, let's say, n flips, assuming we know what the probability of a heads is. Now, of course, the problem is we don't know what that probability of heads is. And implicitly, what we're actually doing is we're talking about a conditional distribution. We're conditioned on the assumption that we know what the probability of a heads is. Flip it. All right, well, let's be a little more precise about what that means. So what that really means here is if you truly don't know, then what I'll say a priori, so that means prior, before you know anything, then a priori, the probability of a heads is some random variable, and let's call it H. And so we know that this is now uniform on the unit interval from 0 to 1. So and what is on this axis here is probability of a heads. Let me see if I can pull up a picture where we've got a coin where the heads maybe not something we're used to, and we don't know what the probability is. I'm going to pause again. So again, apologies for the interruption, but I found the coin that I wanted to talk about here. And I alluded to this at the beginning of the lecture. I said, let's imagine maybe we have an alien coin, and I've seen what is most likely a joke website story of a farmer digging up some dirt, maybe plowing a new field, and they found the following coin on their property. All right, pretty spooky, but I don't think you should take this too seriously. But I want us just to imagine, suppose we did find this coin and we found that when we flipped it, it sort of behaved oddly. And in fact, most of the time, it didn't actually give us a 50-50 ratio of this alien heads versus whatever's on the other side. I don't know. So the coin is, what if it behaves oddly, like consistently less than 50% of the time we get heads. So how would we actually go about sort of proving this, and then sort of saying what our certainty is about how this the probability of a heads is distributed for this particular bizarre coin that might have weird magnetic properties or something? So again, the picture is that at this point you need to throw away any of your preconceived notions. And this is what I mean when I say we talk about a priori, which is the same thing as saying sort of prior to knowing anything. And so this uniform distribution on the probability of a heads, this right here is our prior. So let's suppose that let's say, flip this coin 20 times, or just more generally, let's say we flip it n times, and we get k heads. All right, so now we do an experiment. This is what I mean by our experiment here is now we flip the coin and see what happens. So we know that the probability of, let's say, k heads out of n flips, conditioned on the fact that, let's say, h is equal to p, that's our probability of a heads. Well, this is a familiar formula. It's n choose k, p to the k, 1 minus p to the n minus k. This is our usual binomial formula. And in fact, this is our conditional probability mass function, is this binomial. So what we're seeing here now is a coupling of the discrete and the continuous. Our discrete random variable in this case being counting the number of heads that have been flips. But since we are not sure as to what is the distribution for the probability of heads, right now we're just starting with the simplest uniform continuous random variable, which is a uniform on 0 to 1. So it's conditioned here on a continuous. So let's suppose that we actually flip this n times, let's say 20 times, and we get 7 heads. How does that affect the shape here? So now we want to use Bayes' rule. So suppose n equals 20 and we get k equals 7. How do we update our beliefs about the coin? And in this case, what we're interested in is h. So we're curious how this curve changes. Well, we need to apply here essentially Bayes' rule. So again, Bayes' rule comes to the rescue. So what does it look like in this case? Well, now instead of talking about absolute probabilities, let's talk about probability densities. So again, if ever asked that h have an exact probability, because it's a continuous random variable, we know because this is equal to 0, we have to talk about densities. The conditional Pdf for h. Again, conditioned on Sn equaling k. So in other words, what I'm interested in is f of h conditioned on Sn, where I'm saying that, all right, what's the probability of p conditioned on the information that Sn equals k. Notice this looks exactly like what we were doing earlier, where I said, well, what's the PDF for x conditioned on y equaling a specific value? But there, in that case, both x and y were continuous quantities. Here now, let's think about it, y as being Sn. This is now a discrete quantity. And how does that update our beliefs about this continuous random variable, h? So this is our conditional PDF. Well, if we flip back just 2 slides here, we get something like this. X conditioned on y equaling y, you want to think of this as our Sn equals k, is going to be whatever the conditional distribution for y was, which is Sn, times whatever this probability distribution for x, which is our heads, initially was, but then divided by the probability of the evidence. So it's going to be probability that Sn equals k. All right, so what does this look like here? Well, this now looks like whatever f of, let me call it this way. So it's going to be the probability that Sn equals k. Well, I'll stick to the rule. So this is probability of Sn given h. It's the probability that Sn equals k conditioned on h equals p times the PDF for h before we know anything, and then divided by f of Sn equals k. Now, you might be a little confused here. You're going to say something like, well, hold on, just back here, we talked about the probability. But notice that the difference between probability and probability density for a discrete random variable is there is no difference. So I can actually think of this as f. So let me just go ahead and write that in our case. But for discrete random variables, there's no difference between f and p. So this ends up looking like probability that Sn equals k conditioned on the assumption that h equals p times the PDF for h, divide by the probability that Sn equals k. So actually, we know a lot of these expressions already. So this is the usual binomial. This is our prior, but now we need to figure out what's the denominator. So just to highlight that real quickly. So this is going to be our prior. This right here is our binomial. And so now we're just left with figuring out what the heck is this? Because remember, this is the probability that Sn equals k aggregated over all possibilities for what the probability of a heads is. So we have to basically use the continuous version of the law of total probability. So let's figure it out. So the probability that Sn equals k is going to be the integral from 0 to 1 of the probability that Sn equals k conditioned on h equals p times the probability density for p integrated out over all p. Notice this is exactly the expression for marginalization that we had earlier, except I've gone ahead and blended the roles of probability and f. You should just think of this as f. And then we're back exactly to this rule right here, which looks something like this. Yeah, this one right here. That's the rule we're basically using here. We're using this rule. Again, Pittman calls this average conditional probability. I sometimes call this the law of total probability. Probability. All right, so let's get on with it. So, all right, what does this even look like? Well, remember, our prior here is the uniform distribution from 0 to 1. And I know what this expression is here. So this is 0 to 1 of n choose k, p to the k, 1 minus p to the n minus k. And this is now multiplied by this uniform from 0 to 1, dp. Now, in this case, maybe what I should have said is that initially this integral is from minus infinity to infinity. Similarly here. But the fact that we truncate the integral is because our PDF for P, or H in this case, is concentrated between 0 and 1. So this allows me to then just think of this as the integral from 0 to 1 of n choose k, p to the k, 1 minus p to the n minus k, dp. Now notice n choose k doesn't really make any appearance here. So we can just pull it out and treat it as a constant. So we have n choose k equals integral from 0 to 1, p to the k, 1 minus p to the n minus k, dp. But now a question should emerge, how do you integrate that? How do we integrate that? Again, always in calculus, we give you things that are going to be easy to integrate. But in this setting, this is actually not going to be an easy thing to integrate. In fact, this shows up so often in probability theory, we've given it a special name. And so let me tell you about it. So this is something called the beta integral. And again, it's one of those sort of impossible integrals that show up, like integrating e to the minus x squared. We just end up calling it capital phi for the CDF. We just know that that's something we got to farm out to computers or z tables to do. Similar story has arisen for beta integrals. So this is just a definition that you have to take on somewhat good faith, which is that the integral from 0 to 1 of u r to the minus 1, 1 minus u to the s minus 1 du is given by these gamma functions, gamma r, gamma s, over gamma r plus s. And this is true for r greater than 0 and s greater than 0. Now, what is this gamma function? So remember, gamma here is the continuous extension of factorial to things that are not integers. So like we all know what 3 factorial is. It's 6 because that's 3 times 2 times 1. What's 3.5 factorial? If you try to apply the rule of like, well, take minus 1, so 3.5 minus 1 is 2.5, 2.5 minus 1 is 1.5, 1.5 minus 1 is 0.5, 0.5 minus 1 is negative 0.5, and then you keep going on to infinity. So that's the problem with defining factorial for non-integers, is that if you just try to do the reduce by 1, you get into trouble. But it turns out smart people have figured out how to like make this work. And so for integers r, we know that gamma, let me say r equals n, you know that gamma of n is equal to n minus 1 factorial. This is the usual definition of factorial. All right, well, this integral here looks pretty dang similar to what I just wrote. Let's just go ahead and figure it out. So now let's apply this to our problem. So remember, what we ended up getting was something like is equal to n choose k, integral from 0 to 1. So last page. P to the k, 1 minus p to the n minus k dp. All right, so now let's just try to play a pattern matching game. How do I make this look like this? Well, obviously, I could just set u equal to p. That's a cosmetic difference. I need to figure out what are the exponents here. All right, well, k obviously has to be r minus 1. So let's go ahead and write that down. Okay, so k equals r minus 1. So in particular, I can think of this as r is equivalent to k plus 1. Cool. Similarly, what I got here, n minus k, that has to be s minus 1. So let me go ahead and plug that in. So, and n minus k is equal to s minus 1. So in particular, if I write this as in terms of s, so I get the implication that s equals n minus k plus 1. All right, so now let's plug this all in. So I end up getting gamma r gamma s over gamma r plus s. So this equals gamma r times gamma s over gamma r plus s. All right, let's double check. Yeah, that looks right. All right, so we plug it in. And what do we get? We now get gamma k plus 1 times gamma s, which is n minus k plus 1. And then I need to add these things together. So gamma k plus 1 plus n minus k plus 1. All right, well, I already see that the k's are going to go here. Cool. And now I need to use the fact that this is true. So in particular, when I look at something of gamma like n plus 1, that's just n factorial. So actually all these things here are going to be gamma of k plus 1 is going to be k factorial. So this equals k factorial. And this is n minus k factorial. And then we're going to divide by, all right, what do we got here? Looks like n plus 2 factorial, which is going to give us n plus 1 factorial. And of course, I need to remember that I've got this guy right here that has to come along for the ride. So when I'm trying to evaluate the total integral here, I've got this n choose k from above, and then times this expression. Now, does this expression look familiar at all? Well, almost. If I pull out an n plus 1 from the bottom, I then get the following. So again, I've got my n choose k here. But then I've got k factorial, n minus k factorial over n factorial. So again, n plus 1 factorial is obviously equal to n plus 1 times n factorial. So n plus 1 factorial is equal to n plus 1 times this. Yeah, that makes good sense. All right, and moreover, I know that this right here is equal to 1 over n choose k. So this ends up equaling 1 over n plus 1 times n choose k times 1 over n choose k. These guys end up canceling, and my integral ends up simplifying to 1 over, oops. So this ends up equaling 1 over n plus 1. Holy mackerel. So that took a lot out of me, but it also has an interesting interpretation. So I flip my coin n times and I ask what's the probability of getting k heads. So this is under the assumption that there is a uniform distribution on the probability of getting a heads. What it ends up meaning is that actually the probability of getting Sn equals k is 1 over n plus 1. So in particular, this ends up being a uniform distribution on the possibilities of getting k heads. So weird, but that's exactly what happens because we're looking at a situation where we don't know what the probability of a heads is. And so by sort of aggregating over all of our biases, it ends up canceling out, giving us a uniform distribution. So that's totally weird. That's, I find really, really, really strange. So there's sort of two upshots here. So the upshot here is that if I'm trying to compute probability, so let's say the probability distribution for Sn of k, and I think of this as sort of integrating out p of, of course, probability that Sn equals k, Sn given h, so this is k given p, times the PDF for p, where here I'm looking at a uniform on 0 to 1. This ends up canceling out to being 1 over n plus 1. So I now have that the probability mass function is 1 over n plus 1 for k between n, where these are integers, and it's 0 otherwise, i.e. it's uniform. Holy smokes, that's really, really surprising. But remember, we're doing all of this in the service of a Bayes rule. So let's step back 2 slides here, and we look at what was this? What were we looking at here? We're trying to figure out what's the probability density for the probability of heads being p, h equals p, conditioned on information. Well, it was this sort of top expression, which was a binomial times our prior, divided by this total probability here of getting k heads, which we just figured out was 1 over n plus 1. So then we end up getting the following conclusion. So by Bayes' rule, so this is where we do Bayes. For our alien coin. Well, it ends up looking something like this. So the probability density function of h given that Sn equals k. So this is, I think of this as p because it's the probability of our heads given the information that Sn equals k. Well, it's n choose k, p to the k, 1 minus p to the n minus k, times our uniform distribution 0 to 1 divided by 1 over n plus 1. So we end up having this n plus 1 that comes up top. And this kind of distribution itself has a special name. And this is in fact called the beta distribution. So this, again, if I just flip around and bring this up top, this looks like n plus 1 times n choose k, p to the k, 1 minus p, n minus k. And we can drop this p, but just say that p is between 0 and 1. It's our PDF, our conditional PDF. And again, this, you should think of this, the important thing here is this is a function of p. It's a function of p. And so if I want to look at exactly the setting here, where I'm assuming that, let's say, n is 20 and k equals 7, I've actually drawn this curve for you. I've actually plotted it using Python. So for n equals 20 flips and k equals 7 alien heads, our beliefs about the probability of heads a posteriori, so after, on the posterior, we get the posterior probability distribution. It looks something like this. So this is our probability distribution. And so you can see here that beforehand, you know, we had this nice sort of curve. All right, so this is just me plotting the uniform function. So this is a drawing of the indicator function on 0, 1. This is just the PDF for the prior, which was uniform on 0, 1. What is the shape of this new curve here? Yeah, let me do a better job. All right, somewhat better. This is our posterior here. And this is actually an example of a beta distribution. And so I'm just going to go ahead and copy out of Pitman what the beta distribution looks like here. So if I bring this back and look at 327, this is underneath the order statistics, we get this. And so we now have our sort of final sort of distributions for the semester. And these are called the beta distributions or beta densities. And it looks something like this. So and again, the important thing to appreciate here is that we have this weird normalizing factor, which is evaluated depending on parameters. Sometimes we call these hyperparameters in the distribution.
And someone else had to figure out on a computer what the value of this parameter is. Kind of like with the normal distribution, we have this 1 over square root of 2 pi. But the important thing is that the shape of this curve always passes between 0 and 1, which is exactly what happens here. So these points are always going to be fixed, but the way that this curve interpolates between this shape and then maybe it comes out a little bit longer, maybe it comes out a bit longer, and then eventually becomes a uniform. All of that, this whole family of curves comes about by learning more and more about your coin as you flip. So that if you were to flip this coin, 1,000,000 times and you got, let's say, 0.35 times 1,000,000 heads, that's roughly this value here. This would end up concentrating into basically what looks like what we call a Dirac delta function, which would sort of collapse on saying, I know for certain that the probability of the heads for these kinds of coins is, say, 0.35 or whatever 7 out of 20 is. So that's what this value right here is. This is 7 out of 20. And that, notice, is also the location of the mode of this distribution. And this goes exactly to this belief that once you take in data, you should sort of guess the parameters for your distribution in a way that maximizes the probability of observing that data, which in this case is assuming that P equals 7 over 20. All right, I know it was a lengthy lecture, but there were all these last things I wanted to part to you before you moved on to whatever brings you next in life. And I look forward to seeing you in class and in person soon. Have a nice semester. Have a good break, and I'll catch you down the road.